Hello everyone, my name is Xudong. I'm from the College of Intelligent Computing, Tianjin University. Today I'm going to present a paper called Information Sieve Content Leakage Reduction in End-to-End Prosody Transfer for Expressive Speech Synthesis. Our presentation will be divided into 6 parts. And the first part will give a brief introduction of the background of those expressive TTS models, and we will take the GST-Tacotron as an example. Then we will talk about the flaws of nowadays expressive synthesis models. Generally speaking, these flaws can be attributed to a phenomenon called content leakage. We will refer to several previous methods trying to tackle this phenomenon. Then we would interpret a new method to deal with content leakage, and we shall explain its workflow and its background principle, and we also show our modification to the Tacotron. Finally, we will demonstrate our experiment settings, experiment results, and our conclusions. Let's have a brief view of these TTS models. There are a lot of TTS models based on neural networks. In order to make these models can synthesize more expressive and natural speeches, researchers have proposed two main types of methods to solve this problem. Intuitionally, researchers utilize their experiments to draw some features by traditional methods from the reference audios. There are plenty of valuable features such as pitch contour, loudness contour, and so on. However, the expressibility of these methods is highly coupled with the experience of designers. Meanwhile, it's unsuitable to deal with time-variant signals when the names of target text and reference audios are unmatched. Hence, researchers try to use the specialized submodel to generate a feature vector from the reference audios. And these two mentioned problems are effectively mitigated by the new method. Here we list the pros and cons for each kind of models. If we use models based on manually designed features, we can control synthesized audios more easily, but we have to accept its fate of expressive features. If we use those CTS models with a feature capturing module, it is able to retain more prosodic information from the reference audios. However, there is still not a stable way to control the exact feature we want to extract. Meanwhile, since there is no supervision for the feature extracting module, it brings a potential risk of the so-called content leakage, which is the main theme of our presentation today. So let's have a glance at the GST-Tacotron. Since the GST-Tacotron is the basis of model, current Tacotron does not import any style information. If we want to train a model which can synthesize speeches of certain style, we must prepare a dataset of this style. This dataset is monetarily and temporarily expensive. Hence, the researchers imported a style encoder and an additional GST layer to extract a reference vector from the reference audio. The GST layer is used to improve the controllability. So here we can find the concept of content leakage. We can find a Bell spectrogram synthesized by the previous mentioned GST-Tacotron. We can find that its right part is a little blur. This is caused by the content leakage. This concept is the reference vector extracted by the style encoder contains excess information, which might contain some text information and style information simultaneously, but we cannot know whether it carries pure style information. So generally speaking, this phenomenon would lead to flaws in synthesized audios, just as shown here. We suppose there are two main causes of this phenomenon. First, the training of the style encoder is unsupervised due to the lack of high-quality label data. And second is the proper volume of the output of the embedding model is hard to evaluate and set for this task. We here introduce some methods to cope with the content leakage. First is minimizing mutual information. Since in an expressive TTS model, the style encoder and the content encoder would generate two different outputs, and the content encoder is surely to just carry pure text information. Then we just need to calculate the mutual information of these two outputs. The next is a manner which each other the pure and style vector will be. They also imported KL divergence to estimate the lower bound of the mutual information. We simply show their final formula here. There is another effective method which utilizes an ASR model to guide the speech synthesis model. The author kept the GST-Tacotron model same, but pre-trained an ASR model on the same dataset. Then the author used the same reference audio coupled with many different texts as the input of trained TTS model, but imported the ASR model as an extra supervisor to help the TTS model learn how to deal with the uncoupled text style audio, which is the real-world thing. The final loss function is shown here. Due to limited time, I shall not show more detail of these methods here. In conclusion, these methods introduced extra training costs. Besides, their supervision is hard to evaluate whether it's accurate or not. Due to the problems mentioned before, we propose a new idea trying to balance it. It is our information sieve. The key idea of key intention of this method is trying to use the least computation cores without troublesome supervision. Besides, we do not need to test and set the best volume of each output. This module can be attached to any output in order to show its high reliability. This basic principle can be roughly explained as if the volume of the information carried by the vector is too big, the vector would carry some extra and excessive information. By contrast, if its volume is too small, it would lose some key information. Since it's difficult to directly limit the volume by finding a proper dimension, we could use a time-axis filter to get pure information. Here is a sketch of an information sieve. Generally speaking, we downsample the reference vector at a certain interval along a time axis. Then we duplicate those keyframes to keep the size of reference vector same. Here is the sketch, just a sketch. We use different colors of rectangles to show different timestamps. Let's explain how our information sieve works. Suppose we have a source male spectrogram upper X transformed from the reference audio as the input of reference encoder, and the upper Z is the output of the reference encoder, whose size is upper T times upper H. And the dimension of upper Z directly affects the result of a reference encoder. If it is too big, it would lead to content leakage, but if it's too small, it would damage the quality of the finally synthesized audio. So first, we downsample the upper Z along the time axis upper T at a fixed rate tau, and then we'll get Z downsampled belongs to R to the upper limit of T is divided by tau, then times upper H. So in the Z downsampled, we can keep the key timestamps like tau minus 1 and 2 tau minus 1 till upper T minus 1. Then we duplicate the key timestamps respectively by tau backwards. Then we'll have Z hat is equal to R to upper T times upper H. Finally, we can concatenate the recovered Z hat to the output of the content encoder. Here we show the structure of our entire model. Generally, we keep the structure of our GST-Tacotron except first we use all timestamps of final GRU for the bottleneck layer. And then we use our bottleneck layer, also the information sieve, that is the information sieve to mitigate our content leakage. And then we also use instance normalization to replace the batch normalization used in all the convolutional layers of the reference encoder. Here is the settings of experiments. We use Blizzard 2013, which was recorded by experienced American accent film narrator. And the total length of audios is over 140 hours. We transliterate raw English text to the alphabet form and with double S as stop and the seal as the end of each sentence. We drop all the other punctuations. We cut off all the silence at the beginning of each audio and leave 3 millisecond silence at the end of each audio. And we also use sops to suppress background noise. We use Tesla K40M to change model for about 180,000 steps. Finally, we use a Griffin-Lin vocoder and a pre-trained Milgram vocoder to synthesize audios for testing. We have invited 20 proficient English speakers to attend the subjective evaluations, and we also use word error rate to test whether the content leakage is mitigated efficiently. Here's just an abbreviation of each models. The ground truth, the original GST-Tacotron, the ASR-guided Tacotron, and our modified GST-Tacotron with one single optimization of both. Here we show the result of a mean opinion score in 95% confidence interval. We can show that the ground truth is, of course, the highest, but our SIG model, which has combined 2 optimizations, has also have a good most score. According to our analysis, the fewer flaws in synthesized audios encourage listeners to prefer our new models. But we'll have also to acknowledge that there is still much places for a new model to catch up with the supervised model. Here's the result test of the ABX test. Here the X is the source reference audio, and the A and B are audio synthesized by different models guided by the X with the same input text. We can find from the results that our model is preferred both in parallel and unparalleled experiments. There are still listeners who prefer records, which might be caused by the limited highly expressive audio contained in a dataset. So the general style of these 2 models are a little neutral, but it's quite highly expressive compared with pure Tacotron. We show the results of word error rate. The word error rate reflects the number of text errors in the synthesized audios compared with target text. The lower, the better. And compared with other models, we can find that our models refined by the information sieve effectively have lower word error rate, which is only 40% offset compared with the original GST-Tacotron. Here is the conclusion of our presentation. We can find that information sieve is a simple but efficient method. In subjective tests, it keeps its style transferability. In objective tests, it lowers the word error rate efficiently, indirectly proving its ability to mitigate content leakage. Meanwhile, its structure is simple, which can be transplanted into plenty of models easily. In the future, we will try to apply it to more models and search for better parameters, and then we will also try to build a better mathematical theory to explore why this works. That's all. Thank you for listening.